Okay, so let's look at motion video. So with motion video, what we really have is that we have a number of images that are played back at a certain rate. That rate is known as the frame rate. So as long as the images are displayed fast enough, your eye won't perceive that it's actually a whole lot of images being displayed. And a typical frame rate is about 25 frames per second. So that's a 25th of a second is the time for each of the frames. The thing is that when we're displaying these images, because there's only about a 25th of a second in between, there tends to be not a lot of changes between each of the frames. So in this case, this part of the image is the same as that part, is the same as that part. And the same again, these parts are just the same. So there's lots of redundancy with inside our video and with inside our images changing. Also, the eye won't actually perceive certain things, like a fast change of a small object is unlikely to be perceived by the eye. So what we'll see is that motion video typically looks at focusing on these two features in order to produce a small size, either for playing or increasingly for streaming. So this is the MPEG process that we have. We'll look at the standards a little bit later and why it's called MPEG, but it's roughly the same as what we've seen with our JPEG compression, because it's basically just images and then they are played back at a certain rate. So our first thing is to convert from RGB into YUV. YUV is used for video, but we can also use it in terms of YCB and CR. Okay, so we have a conversion which will allow us to convert between RGB and luminance, redness and blueness. Then what we do is that we convert it into our pixel blocks, and after that we look at motion detection. So with the motion detection, we're looking at the differences between consecutive frames and storing the frame and then storing the difference between the next one. We do our standard DCT as we've seen, and we've got a quantization and some sort of Huffman variable length coding at the end. What we often do is we often transmit a full image, and then in the next view we'll transmit a partial image, and then we might transmit a full image again. So this allows us to keep the streaming rate or the file size down greatly, as we just have to transmit a full image every so often. So how it does that is it segments the image down into what are called slices. And these slices are made up of large pixel blocks, and it is these slices that are used to detect the motion within them, inside the image. Only luminance is used, so only the Y component is used. There's not color. So inside each of these larger slices, there are a number of macro blocks. Y is typically a 16 by 16, and U and V are often 8 by 8, or could even be 4 by 4. We define 4 by 2 by 2 means that there are 4 to a ratio 2 for our Y to U, or we might have 4 to 1 to 1. 4 to 1 to 1 means there are 4 times as much luminance as there is in the U and the V. Okay, so for a pixel size of 352 by 288, that's over 100,000 pixels, we get 16 macro blocks along this way, and 22 macro blocks along that way. So this is chosen because it's divisible by both 16 and 8. And the way that motion detection works is that we look at the previous image and the current image, and we look at the difference between each of the macro blocks. So in this case, this block and this block and this one are exactly the same. So we just need to create a reference back to that block. In this case, we do have a change, but all we have to do is to create a back reference to a previous block because it's now moved from them. So we go through the image and we find the differences between the blocks, and then we can actually code them. So everything here stays the same. So we just send the reference to the previous blocks, but down here we would send a difference between these blocks and that block. Okay, so in this way we can actually just reference a previous frame. So we get what's called an iframe. So the iframe is the full image that's sent. So there's no motion detection actually used, and it's often used as a starting point or as a sync. So if we were to fast forward through a movie, we would go between the iframes. So we might the amount of time between it will depend upon when we can actually sync to our images. We then have a P frame, and the P frame uses a previous iframe as a reference. Sometimes we might want to use a reference to a previous one and also a future one. So we have what's called a B frame. So a B frame can either reference a previous frame that's been sent or a frame that will be sent in the future. Obviously, if we use B frames, then we're going to have to buffer a bit more because we're going to have to remember the B frame and then wait for another I frame to come through, or a P frame. So MPEG-2 was a fairly well-defined standard. It had a number of profiles within it that we could actually use. So high definition TV starts really up here, and this is the lower level sort of movie transmission. So up here we have high definition, 60 frames per second and 1920 by 1152 really gives us our high definition standard. We have a lower resolution here, and then we go right down to 720 by 560 and the smaller frame rates. Okay, so our focus is really on producing the right streaming rate that's required for the transmission. So here is an example one here, 25 frames per second, 150 kilobytes per second is our rate there, and then we have a maximum number of P and B motion vectors in between, and this is the gap in between them. Along with that, we've also got encoding for the audio stream that we have, and then there is the format 422. A standard which is being used fairly extensively now and really replaces things like Flash and AVI is MPEG-4 or H.264. It's been standardized by an MPEG working group and also by the ITU as part of their MPEG group. It has the block orientated compression in it, and it was used extensively in Blu-ray players, but now it's been used by many of the online TV providers, YouTube, and within HD broadcasts. It's a lossy compression, but because it's so good at understanding what it needs to lose, your eye doesn't really see any differences in the actual things that it's actually losing. It's also covered by patents and it's licensed to this company here, and anyone who uses it for commercial reasons may have to pay royalties to this company here. It's also free to use for end users for streaming. Okay, so this is a fairly good standard. We can use a program called FFmpeg to be able to investigate our files. So we can see in this case we're taking a movie here, and the key thing to look at, so there's the bitrate that it's focusing on, so we need to make sure for this movie that we can provide that if we're streaming the video. So 25 frames per second, and there's the main resolution. We can see here we're using 8264, the main standard. And then for the audio, that's a fairly standard MPEG for audio, and there's the rate. So we can see the rate for audio is about 1/5 of that of the video, and that's fairly standard. Video needs about 5 times as much bandwidth as audio does. But we need to make sure that we can buffer the video as it comes in. So let's have a look at this program here. Okay, so we use a program called FFmpeg, and we use the -i option, and the -i option gives us the basic details of the video file. Okay, so you can try these out yourself, but have a look and to see what the basic options are from there. So we'll just try the sample here. Okay, so we can see in this one here, that there's the audio AC3, we'll be covering later. There's the bitrate there that we require for the movie, and there's the resolution of it. Okay, so there's the standard conversion that we're going to be using for our RGB to YUV and so on. Okay, we can also extract certain frames. We can extract a certain frame rate per second. So from the movie, we can actually go and take images actually from it. So if FFmpeg, we define the -r option, and that will define how the number of frames that we actually extract from our movie. Okay, so there's an example here, so we can try and take the number of frames from it there. So we're using the -r option for this. And it produces an output where we get our JPEG images from the movie. Obviously we could go right up to the I frame rate and extract actually from there. Okay, and this is just a small Python program that allows us to do that. Okay, so that's been the coverage of MPEG-4, and let's look at how we can identify an MPEG-4 movie. We often look for the magic number, as we've seen from other files. So the magic number in this case is quite a long one. It's that at the very start of our movie. We look for these characters when we're searching for the stream. Along with that, there is a number of other video files. So we'll have a look at this from a forensics point of view. So this is an example movie here, and we can actually see there's the standard signature for it. We can load up another movie if we want, and we'll always see the same standard starting point there. Okay, so for the other ones, AVI starts with RFF, Flash starts with FWS, a Flash Video, FLV is the letters there, and so on. So if we have a look here, okay, so let's have a look at an AVI file. So AVI file, we can find a whole lot of other things from an AVI in that it has certain commands such as list, AVI, junk, and so on, all identified with certain signatures inside it. But the standard header for an AVI is this part here. Okay, so that's been the coverage of motion video, and as we'll see, we're increasingly streaming video, and it's difficult to notice that it's actually been streamed